My name is Robin Clark, and I am here to discuss the ExtendSim database. The ExtendSim database is an ExtendSim feature which has been around for many years. I want to share with you a few of the advantages of using the ExtendSim database, and hopefully will convince you to become a user as well. In this session, I will first provide a brief history of the ExtendSim database. Next, I want to describe some of the high points of the ExtendSim database feature list, and then the bulk of the presentation will be spent inside of a real healthcare model to show off a few of these features. Then we will have a quick review of our discussion. Finally, I have a few references in case you're interested in further reading. The first generation of the ExtendSim database was released in the late 1990s. The second generation of the ExtendSim database was released in 2008. The reason this history is important is because the ExtendSim database has been used for about 2 decades, and it's on its second generation. It is not just a data repository, but with this second generation, the database has been fully integrated into the modeling environment, and it has a very rich feature set. What I will be showing in this video is just the tip of the iceberg. What you see here will just be a few examples to give you a taste of how it is used. There are many other features in addition to the ones listed here. For a more complete list, please check out the references at the end of this video. The first item to point out is that the speed was and still is a very high priority in its design. The ExtendSim modeling components have very fast read and write access to the data. Using the embedded database does not prevent you from connecting to other data sources. The database can also connect to Excel or Access as well as ADO. Quite often, we will build our user interface in Excel or other tools. Then, when we run our model, it will automatically pull in the input data at the beginning of the model run, interact with the internal database during the model run, and finally export the results back to the user interface at the end of the model run. This gives us both the ability to store model data in an external data repository as well as speed during the model run. In the model itself, all of the modeling components are database aware by having the capability of linking to the database. There is more to this feature than you might suspect. Not only can blocks pull inputs directly from the database and push outputs directly into the database, but we can set the blocks up so that they actually wake up based on when the values in the database are changed, similar to a connector message. In addition to being able to connect to the database, there is also features to help us to scale models easily. For example, if we were modeling a production system in a manufacturing plant, we might have a table that describes the processing times by machine and by product type. If we were to add more product types to the model, that would typically entail adding records to the various database tables, but not modifying the construct at all. Changes like this tend to become simple database changes instead of model enhancements. There is also an Excel add-in which allows the user to make database structure changes directly in Excel. There are many others, but let's start out with this list for now, and as we go through the next example, I will point out a few more important features. Before going into the model any further, I do have to give the appropriate credit to Susan O'Hara, as she has helped me develop the model. Thank you, Susan. In order to set the stage, let us take just a minute and talk about the background of the model, starting with the process flow. When patients enter the emergency department, they will first go through the triage process. This process determines the severity of the patient's complaints. Next, the patients will go through the registration process, where they will provide their contact information and insurance information. Next, the patients will wait in the waiting room until it is time for them to be taken to a treatment room. Low severity patients or patients with minor illnesses will be treated in the fast track area if the fast track is open. Otherwise, when the fast track is closed, then all the patients will flow into the main ED regardless of their severity. The main ED Pod 1 is open and staffed for 24 hours a day. The second pod opens during the early morning, just before the typical morning rush, and stays open until about midnight. Pod 3 opens around mid-afternoon and is the first pod to close in the evening. The hours of these treatment areas is driven by the typical patient volume. The model was developed with the following questions in mind. First and foremost, it is to determine how many treatment rooms are needed for a specific level of patient volume. These treatment rooms are broken down to two different types of patients. Patients with low acuity can be treated in the fast track area when it is open and everyone else seen in the main ED. The main ED itself is broken down into 3 pods. Their operating hours are driven by patient volume. So the model is also used to determine the recommended hours of operation for the treatment areas. The main ED pod number 1 is open for 24 hours a day, but the other treatment areas should be scheduled based on the daily patient volume. Let me introduce you to the simulation model. Registration and triage are the green and blue rooms. The fast track area is the first block of treatment rooms. The main ED pod number 1 is the next block of treatment rooms. Then we have the main ED pod number 2. Finally, in the back is main ED pod number 3. Pod 3 rooms are used much less than pod 1 rooms. Pod 3 rooms are only used at times when it is really busy. Pod 1 rooms are used 24 hours a day, 7 days a week. We have summary charts at the bottom. We have buttons in the upper right corner to control the model, as well as to provide access to the model database. This is a video of the model running. This model runs from 7 a.m. to about midnight just to show one day's volume. You can see patients occupying the room as it is running. Now let us take a look at some of the input tables. These tables are set up for the user to easily modify, and they do not have to go searching for a specific block to place them in. These tables are tucked away all nice and tidy in the database. First, let's look at the patient characteristics. Once patients arrive, we need to randomly assign them an ESI number. Here are the ESI percentages. An ESI of 1 would be an individual with severe trauma. This could be something like a heart attack or an automobile accident. An ESI 5 would be an individual who could have went to their primary care physician, but it is probably after hours, so they had come to the ED. Both the ESI 4s and 5s would be going to the fast track area if the fast track is open. The bulk of the patients would fall somewhere in the middle with an ESI of 3. This is a database structure mode. Here is the ESI probability table. It consists of 2 fields, ESI and probability. This view also shows that there is a parent-child relationship between this table and the list ESI table. We will save the discussion for the parent-child relationship for later. By double-clicking on the table, we can open up the table in the viewer mode. We can see and modify the percentages here. While we are here, take notice of the tabs at the top. I'm going to switch to the Input Data tab. These tabs provide a filter where we can place specific tables onto those tabs. This can make it easy to find important types of tables. Setting the percentages up in a table like this and placing it into the Input Data tab makes it very easy for a user to find and interact with the table. Here is the construct which sets the ESI level on the patients. The random number block shown here is set up for an empirical distribution. The data for the empirical distribution is linked to the ESI probability table in the database. With the link, if the data in the table changes, then the data in the random number block would automatically change. Or, if the data in the random number block changes, then it also will change the data in the table. This link works in both directions. Let's look at how this set block assigns the ESI attribute on the patients. As the patient is traveling through the set block asks for a value through this connection. This connection line is how the set block wakes up the random number block and gets the ESI value. The random number block, being set to an empirical table, is generating the ESI value based on the given probability. Once it is generated, then this value is provided back to the set block. Then the set block attaches it to the ESI attribute on the patient. We have just discussed how the model sets up the ESI on the patients. Now we will take that a step further and use the ESI to set up the lab attribute. The diagnostic probability table contains the probability a patient will need labs based on their ESI level. For example, 40% of ESI1 patients will require a lab. 30% of the ESI2 patients will require a lab. This table also contains information on X-ray, CT, and MRIs, but for this illustration we will only look at labs. This is the diagnostic probability table. We can see and modify the percentages here in the viewer mode. It consists of 5 columns. ESI is in the first column, and the other columns relate to the probability of lab, X-ray, CT, and MRI. Like the ESI probability table, this table also has a parent-child relationship with the list ESI table. We have already discussed how the model sets up the ESI attribute on the patients. Now let's look at the construct for setting the lab attribute on the diagnostic probability table. First, the ESI attribute is set. Next, the item travels to the GET block and it reads the ESI value off the patient. The item travels down a bit further to the SET block, which is wanting to set the lab attribute on the patient. For this to happen, it must ask for a value from the random number block. The random number block in this construct is using a binomial distribution and the probability is coming in as an input. The input to the random number block is coming from the read block, which is reading the diagnostic probability table. It is reading the lab column, and the row number is set by the patient's ESI. If the patient is an ESI of 2, the read block will pull the value from record 2. If the patient is an ESI 4, the read block will pull the value from record 4. The read block in this construct is always reading the lab column. The record connector, which comes from the patient's ESI attribute, is constantly changing the row number from the read block. The last input table we want to look at contains the service times of the various processes. This one is interesting because the service times are actually random distributions. The database has the capability of specifying random distributions in a single cell. Let's look at how this one is done. This is the service time table. Take note of the structure of this table. It consists of one field for each of the processes. This isn't the only way one might structure this table. This table could be transposed so that each process is listed by records. The database is flexible such that the model developer can structure their tables however they see fit. let's get back to the random distributions being specified in a table. We can see and modify the service time distributions by simply double-clicking in the cell. This brings up the Database Random Distribution dialog. This dialog allows you to change the distribution as well as the specific parameters associated with that distribution. You can also add upper and lower limits to this distribution. The advantage of storing process inputs, like service times, into the database is that all constructs have access to the same data all the time. If you construct the model such that every patient room is in its own construct, then you wouldn't want to input the service time for the doctor visit or the nurse visit into each and every room construct. What a nightmare that would be if you would have to go and modify the service time of all 50 rooms if it was to change afterwards. You would want each room to pull their service times, both doctor and nurse visit times, from the one database cell where you put the service time for that process. That is why I prefer to store all of my input data into the model database. Now let's take a look at the model outputs and how we are capturing them. First, let's take a look at the patient log table. This is the patient log table. Take note of the structure of this table. Let's open it up. Each record describes a specific patient traveling through the system. Each column describes a specific aspect of the patient. For example, we are capturing when the patient first arrived into the system, as well as when the patient finally exited the system. We are capturing the patient's ESI level, as well as what treatment area the patient went to. We are capturing whether or not the patient received labs or an X-ray. We can capture each and every detail about the patient as they traveled through the system. What can we do with this data? Wow, what a question. We would be using this table to validate the model because this sort of data is what we should have received from the ED to base our distributions off of. Once the model is validated and we begin experimenting, this table will provide us with all the data we need to do a very detailed analysis of the patients and how they interacted with the new system. That could include things like how long were they in the waiting room or how long did they have to wait on the doctor or nurse. I want to give you a peek at how I am capturing the data for the patient log table. But first, let me say that there are many ways to do this task. For this construct, I am capturing some of the patient characteristics using this write block. I have placed this write block near the arrival process. At this point, I don't know everything about the patient, but I do know a few things like the time they arrived, their ESI level, and what diagnostics they will need during their process. These characteristics can be recorded into the database when the patient first becomes aware of them, or at the end of the process, or at any point in the middle where it makes sense. This is a model design issue. In this model, I have chosen to record those values at the very beginning as soon as I can attach them to an attribute of the patient. This is the patient type result table. It is capturing the results by patient type. These results include the following: the number of patients per day, the length of stay of the patient in the system, the door to doc time, the time in the treatment room, and finally the total value added time. The patient type results table is captured as the patients are exiting through the 3 patient flows. I am using this same table during the model run to plot those same statistics at the bottom of the model. This table is being updated during the model run as the patients are leaving, and at the same time, this table is also being used to do charting in a different part of the model. Once again, this shows the value of using the database. Data can be recorded and stored in one part of the model, and it makes it accessible everywhere else in the model. Let's review a few of the items we saw in this model. First, we looked at the structure mode of the database. This is the area where we can create and modify table structures. We also looked at the viewer mode, where we can actually modify the data. Next, we looked at several of the input tables and how we read the data from those input tables. The ESI probabilities table was accessed by linking the table to the random number block. The diagnostic probabilities table was accessed by using the read block to read the data based on the patient's ESI value. We also looked at the service time table. We saw how we can store random distributions inside of a database cell. Although we didn't see it, the service time table was accessed by using the read blocks to read each process's service time. Next, we looked at several of the output tables. We saw the write block writing to the patient log and storing a history of how the patient traversed through the system. We also discussed in this session the concept of data access from both the input data perspective and the output data perspective. On the input data perspective, the ExtendSim database makes it easy for us when we want to use the same parameter in many constructs. The example we discussed included the service time for a patient seeing a doctor. If I have constructs for every patient room, I don't want to put the same piece of data into every construct. It is best to put the parameter in one location, the database, and have each construct access that centralized data when needed. On the output data perspective, the ExtendSim database makes it easy for us when we want to use model results collected in one part of the model to be used in another part of the model. We saw this with the patient type results table and using it in the plots at the bottom of the model. So those are a few of the features we saw during this session. It was not meant to show all the features, but was intended to give you a flavor for some of the possibilities. As I had mentioned earlier in this presentation, I want to provide you with some follow-up resources for those who are interested in pursuing the database further. I do teach a 5-day class on the ExtendSim database. I not only teach the mechanics of how to use the database, but also the techniques of how to use the database in rather complex modeling situations. The best place to find a schedule of classes is on the ExtendSim website. I also have a few references from the Winter Simulation Conference archive papers. You can download them from the Informs website listed here. The first paper has a more in-depth look at the features we have just discussed, as well as additional features. The last two papers are great examples of users taking full advantage of the ExtendSim database by not just incorporating it into their model, but by using it to create their own application within ExtendSim. If you have any questions or want more information about the database, I would encourage you to contact me or the staff at ImagineThat. If you have any questions regarding the healthcare model that was shown in this presentation, or have other healthcare modeling questions, I would encourage you to contact Susan O'Hara. I would also like to thank you for your time in viewing this presentation. I really hope this has sparked your interest in the ExtendSim database.